Okay. Okay, hello everyone. I hope you hear me well. Welcome to this Parasis webinar. Let's wait a couple of minutes. As I see, people are still joining the session. First of all, we have some minutes late, and sorry about that. We will start in 1 or 2 minutes. Just wait that people are getting online. So Didier, can you please confirm you hear me well and you see my screen, please?
Yes, we can see correctly your screen. Yeah, thank you.
Thank you for the confirmation. Okay, so I think we can start. So just a very short introduction on my side. So first of all, welcome to this Parasis webinar again. Thank you for joining us today. So my name is Corentin Jouvet. I'm sales manager at Parasis for Northern and Southern Europe. So just to give you a very short introduction about Parasis, we are a leading provider of simulation software solution and services for electrification. With our expertise in electromagnetics, power electronics, multiphysics, and system level simulation, CFD, and also power systems. In today's webinars, we will discuss about novel interior permanent magnet machines for electric vehicle application. And to develop this topic, I'm very happy and glad to welcome Professor Ziqian Zhu, who has an outstanding experience and currently leading many activities in the electric machine community, as you can see in this biography here. So Professor Zhu is a fellow of Royal Academy of Engineering, IEEE, and IET. He is head of the Electrical Machines and Drive Research Group at the University of Sheffield in UK, the Royal Academy of Engineering Siemens Chair, Academic Director of Sheffield Siemens Gamesa Renewable Energy Research Center, Director of MIDI Electrical Machines and Control System Research Centers, and Director of Sheffield CRRC Electric Drives Technology Research Center. His currently major research interests include design and control of permanent magnet brushless machine and drives for application ranging from electrical vehicle through domestic appliance to wind power generation. He is recipient of 2019 IEEE Industry Application Society Outstanding Achievement Award and the 2021 IEEE Nikola Tesla Award. So thank you for being here, Professor Zhu. With this outstanding background, I'm sure your presentation will be very interesting. And this webinar will last around 1 hour. So there will be a first part dedicated to Professor Zhu's presentation. And then we will keep some time at the end to answer the question of the participants. So if you have any question at any time during the presentation, feel free to type it into the chat box or the question and answer panel in your Zoom control panel, and we will collect all the questions and answer to the maximum of them by the end of the presentation. So Professor Zhu, now that's all for me for this introduction. Thank you again for joining us, and I think you can take over with your presentation if you are ready.
Yes, I'll try to share my screen.
Sure.
Can you see my screen, right?
Yes, but not full screen. Yes, no, full screen is okay. We can see it very well.
Okay, great. Yeah, well, thanks for your introduction. And I'm Qian Zhu from University of Sheffield. So it's my pleasure to give this JMAC seminar on novel interior permanent magnet machines for electric vehicle applications. Well, first of all, I just would like to introduce Sheffield. Where's Sheffield? And Sheffield, of course, is in UK, and right in the center, actually, you can see there. And it's on the east side of Manchester, and only like a 1 hour drive, but because it's a beautiful Peak District National Park, and then 2 hours from London by train in the north. And well, at Sheffield is very well known for engineering, and engineering we are regularly very often on the top 1 or 2 in the country in terms of research funding. The city of Sheffield itself is a city of innovation, because this is one of the origin of industrial revolution, and also the origin of modern football club and the sports as well. And we have excellent environment and relatively low cost compared with London. And this is my research group at the Sheffield. We're particularly well known globally on the permanent magnet machines and the drives as a leading research group. And we are very proud that we have very strong industry collaborations. I'll show you later. And this is the group, and we have more than 120 personnel, including 15 academic staffs, and among them, 9 of them are full professors. And we, in fact, covers all facts of electrical machines and the drive systems, including power electronics, machines, and control, and energy storage. And but we're particularly well known on the research of permanent magnet machines and the drives. And as I mentioned, we have very strong industrial collaborations. In fact, as you can see there, and our group, we also host actually 7 now, and industry funded research centers, because one of them just signed the contract this week. And also 3 government funded platforms, including Rolls-Royce University Technology Center in Advanced Electrical Machines, and Sheffield Siemens Gamesa Renewable Energy Research Center, and Lomax and the CRC, and also MEDI Group, for example. And 3 government-funded platforms, including EPSRC-funded Prosperity Partnership on offshore wind power, and also Future Electrical Machines Manufacturing Research Hub. In terms of my own personal research field, mainly can be grouped into 3 market sectors. One is wind power. So I'm the academic director of Sheffield Siemens Gamesa Renewable Energy Research Center, which was established in 2009. And we've been developing the novel direct drive permanent magnet generators for offshore wind turbines. Has been very successful. And the domestic appliances, and I'm the adjunct director of MEDI Research Center, both in Shanghai and also at Sheffield, and since 2010. Electrified transportation, that include the electric vehicle, more electrical aircraft, and the faster train propulsions as well. So this is the focus today. I'm going to well, talk about it, and but mainly on the novel machine topologies. Now, first of all, I just would like to talk a little bit about the permanent magnet machines. Permanent magnet machines very often considered as the highest torque and the power density and efficiency machines. Now here, probably efficiency is even more important than the torque density here. One of the reasons is because for the induction machine, you can have very high peak torque. And but in general, permanent magnet machine have very good overall performance. And they used to be considered as only suitable for small well, machines, low power applications. And because before 1980s, it has been expensive and restricted to some special applications such as aerospace, because at that time there's only cement cobalt. But now we have neodymium parallel magnet, so it has been changed a lot. By the way, this statement has been stated in Professor Timmer's book. This is a photo which was taken, and when Professor Timmer and myself gave the JMAG seminar and few years ago in 2019. And but obviously since that, because due to the COVID, we can only, well, I can only give the presentation online. I think last year, in this month, I also did one. And as you can see, nowadays, the application market sectors has been extended very significantly, and including industrial drives, automations, electrified transportation, and the one power generation, domestic appliances. Here shows a couple of photos. It could be in the aerospace, aircraft, and no matter whether it's hybrid or electric vehicle, and or domestic appliances here, and the Dyson's using the vacuum cleaner, and the Midea is using in the washing machine, and and Bosch is using in the lawnmower. And this is the one I'm on the top of one of the direct drive permanent magnet generators, and which is 6 megawatt, and was first installed in 2016. And I'm just standing right on the top of that. So you can imagine the power now, at least at well, a dozen of megawatt. And the largest prototype probably is some more than 30 megawatt now. That's for electric ship. And so the power getting higher and higher. We don't know where the limit, and we're trying to push as high as possible. If we have a look at the permanent magnet machine, when I talk about permanent magnet machine, mainly I'm talking about the layers magnet, and also the neodymium parallel magnet type of machine. And then today, I'm particularly going to focus on the so-called RPM machine, interior permanent magnet rotor. Okay. Now, before that, I would like to make, as usual, make an introduction about the RPM machine. So-called RPM machine, that means the magnet has been buried inside the rotor iron. In this case, the nice thing is because you don't need to have any extra return for the magnet. And now we have the magnet for excitation. And then in order to produce a torque, we must have current carrying conductors. So on the state side, we have conductors there. And then in order to improve the magnet circuit, we need to have iron, or very often we call the lamination, okay, on the rotor and on the stator to improve the magnetic circuit. Because electrical machines, normally we always have one stationary, one rotating. So we also need to have an air gap. If we talk very briefly, that's all for an electrical machine. But it's not as simple as that, okay? There's a lot of variety there. And anyway, here shows one example, the Toyota Prius hybrid electric vehicle RPM motor. And in fact, that cross-section is exactly the same as this prototype. This is a rotor, and this is the stator, and with the rotor inside there, but you can't see anymore in the detail, but that's the winding, okay? Now, if we have a look at what's going on in the world for electric vehicle, the RPM machines, and now RPM machine, as I mentioned, the good thing is it has the general characteristics as other permanent magnet machines, high efficiency, and has very wide operating speed range. That's also important. And mechanical robustness, because you can keep the magnet in the rotor and retain it there. That's quite nice. And very important one is it has a high torque density. High torque density, we normally consider the torque divided by machine volume. But in this particular case, even more important is the high torque per PM volume. That's very important. The reason is because in order to produce a torque, you can utilize the reluctance torque. So together with the permanent magnet torque, that essentially is the magnet produce the flux, then you have current, that kind of torque component there. So in order to produce the same torque requirement, we can reduce amount of permanent magnet. Bear in mind, permanent magnet, we're talking about the layers magnet. Yeah, it's relatively expensive, and there's all the resources quite restricted to few countries, for example. And so it's to reduce the amount of layers magnets is very important, not only to the cost, but also to the environment as well. Yeah, so nowadays we need to consider the CO2 emission and also, renewable. And so this is all important. And here just showed a couple of electric vehicle traction motors. For example, this is a Toyota Prius 210 with a V-shape, as just showed you. It's very, very popular. And this one shows BMW's with the I called I bar. It's because it got a magnet here and a magnet there. And then utilize some reluctance feature there as well. And then you can also find the Tesla Model 3 also using the V-shape. So essentially the same as this one. Anyway. And then that's the latest Tesla, the Toyota's RPM machine, and the double layer. And you can see got magnet here, another magnet here, another magnet there. And also has used the so-called like a delta shape. So you got a one piece I bar there, and then a V-shaped magnet there. And Nissan Leaf also using this kind of topology. And there's quite a lot of novel feature there. But if we have a look at just the focus on Toyota RPM machines, I've been working with them continuously for more than 20 years now, and witnessed their development, and it's very exciting. So started with the I bar and then changed it to V-shape. Well, the reason change it to V-shape is because you can utilize the flux focusing. Yeah, flux focusing. The cross-section area of this one is larger than that. And then use the delta type and to enhance the air gap field, for example. And then one of the generation actually is not in the magnet, but it is in on the winding and the structure, yeah, like hairpin type. And then the latest one, as I mentioned, is like this one. And they all got the features. And then now important thing is all of them, they are utilizing the similar stator, all the same stator. So that means for the RPM machine, we normally need to have so-called distributed overlapping winding in order to utilize the reluctance torque, So this is important. And the more variation are in the rotor topologies. This is a quite common feature for permanent magnet machines. Okay, now let's have a look for the RPM machine. So you can have a variety here, just showing like the influence of the number of layers for the RPM machine. So here only got the one layer, here got two layers, here got three layers, and here got a lot of layers there. And then you can even utilize the lamination, axially laminated, center widget by the magnet, for example. Okay, and in this case, obviously, theoretically, as the number of layers increases, then the reluctance torque increases, and the performance gets better and better. But we need to consider that when the layer of the number of layers increases, then the manufacturing complexity increase, and we need to have a trade-off. On the other hand, in terms of performance, as the number of layers increases, and then the performance, the benefit, the gain you got gradually diminishes. So it's quite saturated. So while the performance is gradually saturated, and then what's the point if we try to put more money for manufacturing? So you can do an analysis, you will find, and from from one layer to two layer, you have quite a significant improvement there. But from 2 layer to 3 layer, you still got some good improvement, but not as big as from 1 layer to 2 layer. Then from 3 layer to 4 layer is almost saturated, not much benefit there. So that's why, in reality, you will say 2-layer or 3-layer. That's a limit. In fact, currently, if you see all those RPM machines still in the commercialization, what I'm trying to say is still less than 2 layers. That's because the trade-off between cost and performance. So that's what we need to bear in mind. Let's have a look at the popular RPM rotors, and already utilized, as I said, in the Toyota and in Nissan and or BMW, or more popular now we call the double V. And important things, not only the amount of magnet material, but also the number of magnets is also important. One of the reasons is because the more the number of segments, you need to handle more segments. That's also related with the labor cost or manufacturing cost. So that's why you can see, for example, this V-shaped one only got 2 magnets per pole, and then this one got 3 magnets per pole, and then this one also only got 2 magnets per pole. Yeah, and then this one got 4. So people try to reduce the amount of magnet segments as slow as possible. As again, is the trade-off between the cost and also the performance. And I would like to just very quickly go through the state side. As I said, not too many, and but still got the same variety there. And here you can see the coil simply wound under the tooth. Yeah, on the tooth. This is what we call the double layer, because you got the 2 coil sides in the same slot, and this one is called the single layer winding, or you can call the non-overlapping winding one. Because this, if you the one here showing actually is end winding, but if you look at the end winding, they are not overlapping each other for phase A itself or A, B, C phases. And this kind of winding obviously looks very neat, right? Very neat. And it's very good for automation because you can make it modular. The end winding is so short, so the effective part can be extended within the same machine space envelope. But one of the issues, this type of machine, normally, it will be so-called frictional slot machine. That means the number of slots per phase is frictional. Consequently, the reluctance torque will be limited. Yeah, so that means you also needed to use more magnets to produce the same torque. Now, in this aspect, it's not so good. Yeah, because you need to use more magnets. But the end wind is shorter. So you have needed to have a good balance, depends on whichever. But in the electric vehicle, in general, this type of machine topology is less used for the main traction machine. And the more popular one is this type of so-called overlapping winding, can be distributed. That means per pole, we have more than 1 coil, or just the 1 coil, which is concentrated winding this time. Now, this is because the coil pitch, you can see, is almost equal to the pole pitch. You can see here from here to there, that's almost a 1 pole pitch. So you can utilize the collective, the flux all produced by that magnet. But more importantly, if we utilize the RPM load, this is SPM load, only for illustration for the state winding. Now, if you utilize the RPM load, then you can utilize the reluctance torque. Now, this is very good. So reluctance torque is good. You can reduce amount of magnet, but this one got a longer end winding, okay? But overall, as a trade-off, the gain you got for the reluctance torque and then the demerit of longer end winding is a good trade-off. So this is more popular. Of course, there's a lot of other performance. For example, is the high speed uncontrolled generator fault, for example, and then this one is better because you utilize less magnet, then consequently the EMF will be lower than the other type. And then in case the inverter failure, the induced EMF is lower. So the inverter is safe, the DC link side is safe, for example. There's a lot of others in there. I'm only talking about the main part. Now, I'm going to start with my main topic, okay? But before that, I would like to talk about what is the torque production in the RPM permanent magnet machine. As I mentioned, in the RPM machine, we have two torque components. One is called the PM torque. One is called the reluctance torque. Okay, reluctance torque is nothing to do with the permanent magnet here. Okay, so even you don't have any magnet there, the machine still can learn as a reluctance torque. But with only reluctance torque, you normally have lower torque density compared with the PM machine, and also you have poor power factor. So this RPM machine has the synergy of both machines, and they can utilize less magnet and then utilize the reluctance torque. The PM torque here expressed like this. So this part is the PM torque and the conventional. It's essentially flux produced by magnet and then times the current. That's the power and the force or torque. And then another one is pure reluctance. You can see the angle here. The reluctance torque here, you got twice of the angle there. Okay. So this is okay. If you just plot this PM torque and plot the reluctance, it's something like this. PM torque is like that. Yeah. This is a current. That means zero means that EMF and the current, the phase angle is aligned. So it's zero. And then maximum is always when the EMF aligned with the current, you got maximum. Reluctance torque is a bit different. Reluctance torque is somewhere the maximum is about 45 degrees. So you can see the angle difference between the PM torque and the reluctance torque, yeah, for their maximums here is somewhere here. Typically is 45 degrees. Yeah. Then if you would like to increase the torque of this RPM machine, obviously, I listed here. One is to increase the PM torque. Another one is to increase the reluctance torque here. But today I'm going to talk about is a little bit different. Yeah, I'm going to talk about to change the angle here. Yeah, you can see the angle. The maximum here, we try to utilize another freedom, okay, to increase the torque. That's everything. Okay, so the remaining, essentially, I'm only going to show examples. Yeah, but before that, if we want to increase the PM torque and reluctance, how do we do it? I just very quickly highlighted that. So in order to increase the PM torque, as I already mentioned, you can utilize the flux focusing by employing V-shaped magnet. And here showing is even more using a U-shaped, yeah, U-shaped to utilize the flux focusing. Therefore, you can have more flux produced in the air cap and to link with the stator coil, and then produce higher flux linkage and consequently back EMF waveform, yeah, magnetomotive force. But in this case, obviously, you are using more magnet material, you are using higher number of magnet segments, so you need to bear in mind the cost, because the more cost you put in, you need to bear in mind that the vehicle performance is getting better, maybe, but if you're making the machine, your profit is reducing as well. Then you can also try to increase the reluctance torque. Normally, essentially, you try to increase the number of layers to increase the so-called sealing ratio. That means it's the D-axis and Q-axis inductance, that ratio. But as I mentioned early on, as the number gradually increases, then that ratio gradually diminishes. So typically we're using 2 or 3 layers. Okay, that's very, very common. Okay, now let's go for my main topic. What we try to say is the technique we are using a terminology called the magnetic field shifting techniques. Okay, so essentially we try to change the angle between the peaks of PM torque and the reluctance torque to enhance the torque. By doing that, we needed to introduce a so-called asymmetric RPM machine techniques. Let's have a look, okay? First, I would like to compare with the conventional RPM machine. So conventional RPM machine, essentially, you don't have any shift. Now for this one, we try to introduce an angle. So this is so-called asymmetric RPM rotor's shifting angle. So what's happening by doing that? This one I just showed you early on. Okay, so I'm going to only talk about this one. So you have the PM torque here. You have the reluctance torque there. Their peaks has the position for that current angle, yeah, has been shifted, or related with the rotor angle has been shifted. It's the same thing. Okay, one is in the time, one is in the space. So now the PM torque is here, and the reluctance torque is here. So that bit angle has been changed. By changing the angle, we try to make the resultant PM torque and the reluctance torque, the summation, bigger. So you can see here, this one, normal symmetrical RPM rotor is here. Then this one is here. Yeah, and this is the fundamental principle. Now, important thing is we have shifted their angle and changed their peaks. Objective is to get the resultant one higher. But we have a condition. In all my later presentation, I have a condition. The amount of magnet remains the same. We keep it the same. So that magnet amount, the cost is the same. Okay, now just to have a look how we can realize this so-called asymmetry. There's quite a famous the topology proposed by Mitsubishi. Okay, so this is what we have there. And you can see this is essentially a V-shaped. Yeah, V-shaped. We got this side and that side, but both sides they are not symmetrical. Not only they are symmetrical, but importantly we have a flux barrier there. Because if you use a V-shape, you utilize the asymmetry without that flux barrier, not much difference from the symmetrical, because the flux ultimately they all go to the same place anyway, focus onto there, the same. But by doing this, by introduce this flux barrier, we can modify the air gap field distribution, shift the fundamental air gap flux density, you know, by shifting it, then we can change the angle. This is a simple principle. And in fact, if you try to look at that, you have a variety you can do. For example, you can have a PM configuration, yeah, asymmetric one or symmetric one, or the rotor core geometry, or you can call it the flux barrier. There can be symmetrical or asymmetrical. Then together, you can form a novel asymmetric RPM machine topologies. As I mentioned at the right beginning, PM machines, there's a lot of variety there, although it looks like simple, only got magnet, iron, and copper. But we have a lot of topologies. So even here, we can have a lot. But how do we define those machine topologies? We have proposed a simple technique, okay? By utilizing the 4 quadrants, and the one side is the rotor core, the flux barrier. Yeah, whether it's symmetrical or not symmetrical. Yeah, so this side, the rotor iron structure, they're all symmetrical. And then this side, they are asymmetrical. And another axis, y-axis, is the PM configurations. This, the top side, PM configurations are symmetrical, and then bottom one is asymmetrical. Yeah? Let's take one example. If you look at iron structure here is symmetrical, yeah. About the axis of the pole, they're symmetrical. Symmetrical here, but this side is not symmetrical. You look, this got a little bit there, not symmetrical. This side is very obvious, not symmetrical. But if we look at the magnet, for example, here, symmetrical, yeah, symmetrical, but asymmetrical. Now let's have a look at more detail, right? So this is the overall. Now let's look at that first quadrant, because the first quadrant and the globe here, the globe is symmetrical here, symmetrical here. So you can have a combination, you know, 2 combination in total 4. So just to look, focus on this. So the magnet should be symmetrical, and then the ion structure should be symmetrical. So here you can have this and that. So how I utilize it? You utilize the 2 rotor. One part of the rotor is like this, one part of the rotor is like that. This is only just for illustration, simple. You got variety, I'll show you later anyway. Yeah. And then another one here, obviously, is here. You can see there the magnet is symmetrical, but the ion structure is asymmetrical. Now, in this case, it's quite similar to the V-shaped RPM rotor. Apart from that, on the V-shape, we have a little bit extra there as a flux barrier. Then by doing that, shift the angle. And then we also have this ion structure symmetrical, but magnet not asymmetrical. So you can see among that symmetrical ion structure, we essentially have inserted a asymmetrical magnet there. Yeah, you can see here the color as shown here. And then another one here, the ion structure is asymmetrical, magnet is also asymmetrical. This is simple, but very, very useful. I can point out that to you. In reality, when the ion structure, when the magnet structure, both of them are asymmetrical, will be the best. In fact, we proposed quite a lot of the structures in this quadrant. So it's quite useful to guard the designs, right? Now let's have a look one by one, okay? Each of them. So first is the symmetrical PMs and the symmetrical rotor core. Yeah, and so essentially you can try to utilize 2 rotor on the same shaft. So it's still quite simple, it's not that complicated. Yeah, but the relative position between this PM rotor and the reluctance rotor can be shifted. So you have a freedom to change it here. In fact, this topology was well developed a long time ago, developed by Professor Brian Chalmers at Manchester. But at that time, they didn't consider this torque enhancement, but they mainly considered this how to improve the flux weakening capability. Yeah, so their machine is not, although it's the same, but they didn't consider this angle for the torque enhancement. And so it is slightly different. And in fact, in this case, you can say on the rotor part, you may have 2 rotor part or 3 rotor part to make it actually more balanced. Yeah, and then on around the axis, not necessarily you need to be identical 2 parts. You can optimize the PM torque, reluctant torque, the component. So you have at least, in addition to conventional rotor, you also have 2 more freedoms, right? One is the portion around the axis. Another one is the angle between 2 rotor. So you got more freedom to optimize the machine. Now, in terms of the topology, as I mentioned earlier on, I'm just showing one is the surface mounted, another one is just pure reluctance. So obviously, you can have any type of the PM rotor or RPM rotor as well. Now, this one is even memory machine, for example. And then you can have a spoke type as well, or any other type, a good combination there. So a variety there. But among all those machines, if I just typically showing here, this is with the 2 parts equal, equal type, and then they got 3 portion and also 3 portion where the reluctance rotor is in the middle or at the other side. But honestly speaking, by doing that, you definitely will get good torque improvement. Yeah, in my opinion, it's quite good because Linearization is quite simple because if you look, each rotor is conventional. Just introduce two optimizing the parameters there. Then this is about the power for the flux weakening capability anyway. So they also medium, I will call it. Right? Then memory machine, of course, it will have more, but that's because of memory machine itself. And then the torque ripple reduction, and you have quite a few freedoms there. Usually surface mounted one is a bit easier, and that's why I put a little weight on that there. So. And whether you have the axial balance or unbalancement kind of thing there, so depend on the structure. If you have the structure of two portions different, of course it will cause unbalance there. And then this side, even you have the same, but the one is magnet, one is electron, also not. But this side is definitely balanced. Axially is symmetric. Yeah. But in terms of the structure complexity, and it depends on which point of view you talk about it. Here, I put it on the clause. What the reason is you need to make it two rotors. But apart from that, it's quite simple anyway. So it depends on which way you look at it. Yeah. Okay. And then we'll have a look at another one, which is symmetrical PM, but asymmetrical rotor core. Yeah. This case, we only utilize one rotor to realize this magnetic field shift. Okay. Symmetrical magnet, you can see the symmetrical magnet, the symmetrical magnet, and symmetrical magnet, all of them symmetrical. But here, clearly you can see the asymmetric ion there. Asymmetry, a lot of asymmetry you can also see here as well. Anyway. But here you can see the ion cavity or flexibility, they are not symmetrical. This one is towards outside, this one is towards inside, this one is somewhere here. It's like that Mitsubishi one. Okay, I'll talk about more later, don't worry. Then this one, you have the symmetrical there, and then but the barrier, something like that there. And then when it's spoke one, you can ship it. Well, this one and that one, they got some similarity there. Okay, just a different realization there. And some of them you probably found is quite popular already there anyway. Okay, and then again you can compare this torque increase. Yes, they can increase, no problem. Yeah, shifting effect, they're all there. And then this one is interesting, very well known Mitsubishi one. I'll show you later. The effect is quite small. Yeah, not only founded by us, but also founded by other professors, Japanese professors. I attended one of the ECC conference. Professor Yamasaki, he presented a paper. He was quite disappointed that the effect is quite less. Then I'll show you the evidence later. Yeah. Then torque ripple, of course, depend on how many freedoms. And to be honest, all the machine you can try to reduce. Just which one is easy to realize, because this one, as I mentioned earlier on, you can simply just do a shaping like that. So it's quite easy to realize it. And then unified PMs, that's quite important as well, because that means that you can use the same size of magnet, you can reduce the cost. And then in this case, all of them, they're very good because you have symmetrical PMs there. When you have symmetrical PMs there, that means in all the rotor, all the magnet, the size is exactly the same. It's a lot cheaper. Or if it's different, then you need to make different one, then that will be more expensive. And structure-wise, they are quite simple anyway. Yeah, apart from that one, mechanical structure is one of the problem. I think we developed this one as well. And but performance-wise, okay, but we find that the mechanical side is more challenging, for example. Now we move on to the asymmetrical PM and then symmetrical rotor cores. Now in this case, you can find, and if you try to make the asymmetrical inside the type of machine, it's quite simple because we just make the air gap here is different. The magnet shift the related to the inside the type of machine. Okay. Now in this case, also the same way, but this is another machine topology itself is different with the surface and the RPM combination. So you can also just shift it there. And then you can also utilize the hybrid magnet type. Now, in this case, one side is neodymium barrel magnet, and then one side is ferrite. So to make it asymmetric, okay? But you do need to be very careful, in my opinion. Looks like that asymmetric alignment is fine, but in reality, in theory, this ferrite or this neodymium barrel magnet, they produce a flux, they all go to the egg, it's a resultant one. So in theory, without any asymmetric alignment, without the saturation effect, this is still symmetrical in the air gap. So you need to be very careful. Or you can think of in another way, this type to make asymmetry could be not so effective. Okay. Now this is the same. You got the double layer there, but the important thing, you also have another one there. Okay, another small magnet there. Then this are the no magnet, and then try to make it asymmetry. Yeah, try to make asymmetry. So as I said, you need to be very careful. If no saturation, if the magnetic circuit is linear, this is still symmetrical. But if it's saturated, very often this will be more saturated than there, then that will cause the asymmetry. Okay, it's the same here. Now, if you look here, we consider torque, yes, can be increased. The magnetic field shifting, yes, we can realize that. And the important thing is, very important, is about the unified PM. Because, for example, this one, you got a two type of magnet there, this type and this type. But that one, you also have two type there. But this one, all the magnets got different size in one pole, and this one the same. So that could be costly. A lot of people, when they design it, they don't care about this one. This is a problem. If you look at existing commercial products, we will find that they all are identical. Why? Simpler. Yeah. And the structure complexity, we also need to consider as well. Obviously, these two parts are simple. Yeah, this is the simplest. Then this, after this, then this has become more and more complicated. So we need to bear that in mind. When the machine structure is too complex, the application will be limited because you also make the manufacturing cost expensive. This is why I always encourage my students at least think about simple way, not complicated way. Yeah, make it complicated. You can write a paper, but that paper is not very valuable because in reality, it's not be able to be employed. Okay, now the last one we try to introduce is asymmetric PM and asymmetric flux barrier, the load core. Now, in this case, you can say here it's a V shape more or less, but one side, the other side is different. One side, there's no magnet, so only one magnet. Simple. And then another one is a hybrid one. You can see here 2 layer, here 1 layer. Yeah, here 2 layer, here 1 layer. And then this one is one of the magnet has been taken off. This is all proposed by us, and yeah, I'll show you more. And this one is a combination of the spoke type and the V shape, and then together with asymmetry there. Now this is important. Without that asymmetric bit put in there, the machine is still symmetrical. Okay, and so this is a mixed radial and the circumferential one, and this one is a multi-layer one. You put the magnet asymmetric there. But to be honest, it's terribly complicated. By doing that, as I said, if it's a linear, no difference. But this one, yes, has asymmetry. It's not produced by this part. It's produced by their bit. Can you see there? They got a little bit of flux barrier there. To me, it's horrible anyway. Okay, it is a machine, but I wouldn't use it anyway. Okay, let's have a look further in the comparison. The torque increment, yes, you can increase, and I'm not telling you how much. I'll show you the detail later. The magnetic field also can be shifted as well. Torque level reduction, when you use multi-layer, you do need to be very careful anyway. And then in terms of magnet, whether there's a same size one, this you can use just 2. But that one is the best because the reason is you can have this magnet, that magnet, all have the same size. Very good. And this one is slightly less because you can't make this one, that one the same. But in theory, it's not too bad as well. It depends on the design. Yeah, the structural complexity, definitely that one is more complicated. Okay, this one is about the mechanical integrity. It's a bit more, but this is that easy. Okay. Now we have 4. So I would like to put them all together. Let's talk about it. Okay. And let's move it here. Okay. Now in this case, and I don't understand why I have one cursor is keep moving automatically. I can't figure out yet. Last time I tried to remove it, I can't. Excuse me. Okay. So I've put it down here, the global one. You got that essentially two rotor. Okay, 2 rotor there. And this one, and you can evaluate it all there and evaluate it. I just try to put as much as I can anyway, but I've talked about those all in detail. But after that, I'll try to look at the performance, detail the comparison. I think this is quite important. I'm sure principally you understand that already, right? Now let's have a comparison. So what I'm trying to do, I'm taking the Toyota Prius as a baseline. So vast majority dimensions, they're the same. Okay, same stated design, same rotor diameter, air gap, and then same magnet material and also usage. Okay, all this is the same. Now let's have a look. This is the topologies which I'm going to compare, reference to the Toyota Prius. So I have selected the 6 machine topologies. Among these, 3 of them are proposed by us at the Sheffield, okay, by my PhD student, Dr. Yang Xiao. And this is the one already existing in the literature. I just quickly highlight again. And this is a combination of SPM and V-shape RPM. And this one is V-shaped one, but with asymmetry cavity. And this one got 2 rotor combined with surface mounted and RPM. And then the one we proposed here essentially is this hybrid that spoke and the radio one, but with asymmetry there. You can see asymmetry and also asymmetry there. And here we got essentially one side is a single layer, one side is 2 layer. And then one of them is with 2 small magnets inserted in 2 cavities. And then this one only put the magnet into one of them. Okay, I will compare with another one with the magnet only this side. Okay, because that's a Mitsubishi one. I'll compare separately. But let's compare this 6 first. Now, for all those 6, I'm showing that structures here again, just for simplicity. Okay, so first of all, what you can see is here I'm showing the resultant torque, that's a leather color, and then the PM torque, which is that blue one, dark blue one, and then the green one is the reluctance torque. So you can see all those machines, you have the reluctance and the PM torque there. Amount of magnet the same, right? Don't forget. Okay, now it's quite interesting. I'm not going to talk about that one because that one essentially is reflected here and it's the same. Okay, so that just showing when the current is small and then until very large, what's happening. And they are very consistent. I don't see crossover too much. There's a couple of them crossover, but not too much. So let's just talk about this one. So in this case, let's compare with that this machine and that machine because they are next to each other. Very interesting. You can see this machine compared with the Toyota Prius, the PM torque is less. Here and there. So PM torque is less than the Toyota Prius. Reluctance torque is also less. Yeah, reluctance torque is also less than Toyota Prius, but the resultant torque is higher. Yeah, so this clearly illustrating the effectiveness of magnetic field shifting. Yeah, PM torque is less, reluctance torque is less, resultant is higher because we have optimized the angle between there. So this is quite interesting one there. And then next one is this one. Yeah, it's a V-shaped one, but simply based on that, we introduce a little bit asymmetry there. Yeah. Now in this case, you can find the PM torque is increased slightly, almost the same, but this reluctance torque is increased compared with that. And then the resultant one together is also higher. Yeah. Here is higher than this one, another one. So very similar manufacturing, you know what I mean? Only slight change in lamination, but then you can get it again. Fantastic, right? Very good. And then the next one is this mixed up one, you know, SPM, RPM one. And again, it's a very interesting one. Typical. This one, the reluctant torque is less, but PM torque is more now. Yeah. Then the resultant one put together is also higher. So this is another case. Okay. Then if we look, those three machine topologies proposed by us at the Sheffield, all of them produce the highest torque, higher torque than others. Why? Because we have utilized the asymmetric PM, asymmetric also iron flux barrier as well. So this, the core in the coordinate, the third quadrant is the best. So this is our machine. Now this is also interesting. The reluctance torque is almost the same, but PM torque is increased. Then the resultant torque is higher. And then this one, the reluctance torque actually is less. Yeah. And the PM torque is also less, but the resultant one is better. Yeah. And then this one, the reluctance is a bit less, and then the PM torque is a bit more, but then the resultant one is the highest. Is the highest. Fantastic. We're very happy, right? With minor change, and you can improve the performance there. Here, just showing the EMF waveforms and also the torque there. That torque you already seen early on. Why I'm introducing this one? Because I think it's also quite interesting. I'm not comparing the EMF harmonics. When you can try to reduce it separately. The result I'm showing here, we didn't consider this, but you can do separately and quite easy. But important thing is whatever you can see here, the resultant torque here from the left to the right, the left is always the best. But if you look at the EMF, it's not like that always reduce, and then the total torque is reducing gradually. But here it's going down, up, down, up, down, quite a bit there. So clearly showing here that EMF is only one part, because we have the reluctance torque there. Also, we have the another freedom is the angle of the peak EMF produced torque and the peak of the reluctance torque there. Yeah, this is very interesting. Now I'm going to do another comparison. Yeah, a comparison of the Mitsubishi one and the one we proposed. The difference actually is quite interesting if you look at it, quite minor there, because the Mitsubishi one essentially trying to make the field distribution asymmetric, so introduce the flux barrier inside the V shape, so you can change the angle here and here to make it asymmetry. And then this one we make essentially is opposite, so you can think about that angle is keep changing. It's like a continuous. So it's the same family. You just go further. Then that's the result we got, the peak torque. Now in this case, please bear in mind that the state is exactly the same. Nothing else changes. Just a bit inside the change it, while maintaining the magnet volume the same. Okay. So this is also quite interesting. Now, if you look at the produced average torque there, you'll find when the angle changes from here gradually beyond there. So this side essentially is based on Mitsubishi's topology. This side is based on our topology. So what you find is you can see the torque overall. Here you have a peak there, then I can also have a peak there, the optimized one there. This side is much bigger, much bigger. So you see, at the right beginning, I mentioned the permanent magnet machine is very simple, iron copper magnet. But by this subtle change, you can improve the performance quite significantly. This is why we need the electrical machine, permanent magnet machine designers, right? So this is quite interesting, showing clearly. And the manufacturing is similar, magnet mounted the same, performance is better. Yeah. And by the way, we have patented all those. Okay. Those are mentioned, proposed by Sheffield. We all patented. And now here I try to make another comparison. Okay. And detail the thing there. And I think here try to compare this performance. One of the reason is because I mentioned that with the asymmetric cone, we got some good performance there. But in this case, what I'm trying to do, another comparison is this asymmetric, this side is one layer, this side is two layer. But with the two layer this side, I can put the magnet all there, or no magnet there, or put the magnet this side, or put the magnet that side. Right? As a 4 combinations there. Now compare the performance. Again, as I mentioned, that the total amount of magnet are the same among all those 4. So you can see you don't have magnet there, but this piece of magnet is already bigger than others, right? It's a bit obvious, you can see it, because we optimize under that condition. Now in this case, what do you find is if we look at that average torque, okay, the total torque, which one is the best? This one is the best. Yeah, this one is the best. Okay, and then this one is the second. Clearly put the cavity outside is better than the inside. Right? You can see that. Quite interesting. If you take the magnet off, then definitely it is the lowest. This is quite interesting. Of course, among all those, you can also look at what's the components of PM torque and also the reluctance torque. And then you can find that obviously this side is better. Okay, the PM torque. This is similar. Okay, and then you look at the reluctance torque. This one is the best. Yeah. So very interesting. If you look individually the PM torque, if you look individually the reluctance torque, the Mitsubishi one is the best. Yeah, but in terms of total resultant torque, what we proposed are much better. Yeah. Why inside this all reflected into that angle shifting there? So it's a vector. Yeah, it's not just the numerical added together, it's a vector sum. Okay, then result in the difference of the total torque. So this is very interesting in my opinion. Of course, I normally don't like to make an experimental validation or something like that. I personally feel accepted for very new machines, and then you might have accidentally and measured predicted. Finite element is very well established, right? JMAC is excellent software. We trusted it, and a lot of my students at the Sheffield are using JMAC. There's of course other software as well, but JMAC is excellent software. And normally, if you try to make a prototype to make a component, you usually get a good agreement. Anyway, okay. And here it's not the different other anyway. So I just show you the result. You can say for this one, you can say asymmetry, 1 layer here, 2 layer there, got 2 little pieces of magnet there. The lamination looks like this. Okay, and then you got the line EMF there, the agrees very well there. Okay, and then if you consider the static torque is like this, and then that's the torque against the rotor position. And although the measured one always will be smaller because the final element is 2-dimensional. Okay, and then that's the torque against the current. So very good agreement there, in my opinion. And of course, if you try to calculate the 3-dimensional, and it will be even better. Okay, but I think that's really already very good. It's clearly showing the principle works. And this is showing another machine which we have taken 1 piece of magnet off, so only got 1 magnet there. Okay, and then that's the EMF, that's a static torque, and the measure the static torque and the EMF in 3 phases, and also that's the torque against the current. Again, it's a 2-dimensional finite element. and also the measured result actually is quite well. Okay, so I think this is towards the end of my presentation, and I'll try to make a simple conclusion. Okay, essentially showing this magnet field shifting really works. Okay, it can produce increase the torque by changing the peak PM torque and the peak reactant torque, the resultant vector resultant torque could be higher. Then there's a variety of topologies. I showed you already a lot there. Then we also have proposed a method to categorize it and to easy understand according to the symmetrical or asymmetrical alignment of PMs and the cavity. And also, I showed you there's a lot of machine topology there, particularly those machine topologies proposed by us with simple structure, improved torque capability. Okay, so I personally think this one got a very, very good opportunity to be applied into the electric vehicle. Now, we needed to bear in mind, and this one got the asymmetric rotor. You might going to ask me a question, so I'm going to answer in advance now. So how about the forward rotating, backward rotating? The answer is forward rotating is always better than the backward rotating. But it depends on, are you going to drive forward more or you're going to reverse more? I think for electrical vehicle, apart in the parking or in the garage, you do reversing. Most of the time, you're always driving forward, right? Okay, thank you very much. That's all from me.
Thank you, Professor Du. Thank you very much for the very nice presentation. So now we can take some time to answer some of the questions. So for now, we have one question. So Professor Du, you can open the Q&A panel if you want.
Q&A, where to find? I got chat there. Or you can read out for me.
I will read them.
I can't see the Q&A.
Okay, I will read the question anyway, so you know about which one I'm talking about.
Q&A, I saw the Q&A now.
Okay.
Yeah.
So hi, Professor Du, thank you so much for your great presentation. I have a question about ASIPM machine you showed, the one from your group and Mitsubishi. Would you please explain about the barrier shape, especially the tangential ribs? There are two-layer ribs. Can you explain the reason?
The two-layer ribs, because you needed to have that at the outside of the rotor and also inner side. You do definitely need it. That's the same for the for any RPM machine. I'm not too sure whether you're talking about the ribs. Is that because I'm using two-layer cavity? And the two-layer cavity, because essentially you need one is to make that field distribution more asymmetry. If you use only one cavity, and then as I mentioned, if the magnetic circuit is linear, even left side, the right side, they are different like that, right? All the flux, this produced good there, that produced there, no difference anyway. Because it's inner, that you have the iron as the flux gather, and then they all gathered to the same place. So there's no asymmetry, even the magnet allowed. So by putting a barrier, like that, yeah, and then Mitsubishi is trying to do this side, this side, and then that side, not the same amount of flux. Flux density is different, so the peak will be shifted. So what we're doing is we put it here. So the amount of flux and the amount of flux or flux density here and there, they're different. Then make it a shifting. Okay. I don't know whether I answer your question right, because you mentioned about the two libs, tangential libs. But libs, because in any case here and the bottom here, you need it because to keep the magnet there. Otherwise, it's going to fly off. Okay.
Okay.
Efficiency. Yes, we investigated the efficiency. The next question is about have you investigated the efficiency? Yes, we do. We have investigated efficiency. This is excellent question, by the way. I really like it. And in fact, the supplement what I have just talked about it. And because when you have the asymmetry there, you're bound to have some harmonics produced. When that harmonics produced, it will increase the ion loss, right? And then in theory, that's bad. It is bad. But meanwhile, you also have increased the torque. So it depends on the portion which you created the loss and also the total resultant torque. And the answer is that increase in the torque is more than the loss produced. Yeah, it's not just the amount, it's a ratio, right? Efficiency is a ratio. And so efficiency is still improved as well. So that's an excellent question. And wait a minute, would you please show the Mitsubishi motor? Okay, Mitsubishi motor, I think just to, I don't know whether you want to see the closed session or you just, as I said, this conventional one, if we look, is like that, yeah? Symmetrical. And then if you make it asymmetrical, it's like that, right? That's one piece of magnet, that's one piece of magnet. Then Mitsubishi one is put a flex barrier in between that V shape. Then the one we proposed, we put the cavity outside. Okay. And
thank you. Yeah, the coin is
the tangential ellipse divided into two parts. That's because we want to make it more asymmetry. Make it more asymmetry. Because by doing that, definitely is a lot more asymmetry. Because as I said, if you only have one, looks asymmetry is not asymmetric at all in the air gap. You only look at the cross section is asymmetric, but not in the air gap. In the air gap is still symmetrical. By putting here and putting there, that's quite important. Yeah. And the Mitsubishi is nothing wrong, just there it's not so effective. We found the put oxidizer more effective. So that's quite important. And if you look at all the topologies I mentioned, apart from the one in the first quadrant, they're all symmetrical. All others need to be symmetrical, make it as asymmetric as possible. Okay, there's another question there. Oh, sorry. Yeah, thanks for presenting. Your focus mainly on the maximum torque per ampere. That's right. And how about the maximum torque per voltage at high speed? And you are right. I focus more on the torque, but I did cover a little bit there. It's a constant power region. That is relevant with this one. Okay. Now for that one, why I don't focus on? Why I don't focus on, as I said, I do have the result, some PowerPoint is showing there, and then probably I didn't focus on it. But the important thing is because for the maximum operating speed, flux weakening, and or maximum torque per voltage, that side there, you can see the principle lies is a balance between the inductance and the flux linkage. Yeah, the balance. Well, we know if we want to achieve infinite speed, then it's a ratio of the R D I D divided by per C M. Okay, so that means the inductance is important, and also the PM amount is important. Honestly speaking, you got more freedom now anyway, because you got a high torque. Essentially it's a balance between EMF and the inductance. So that is not directly linked with this, but linked with all associated with all RPM machines. So you have another way to specifically design it. There's no problem. Our proposed machine, they all have very high flux weakening capability. Okay. And so which one is now? Do you investigate the vibration also? I'm sorry, we don't. we haven't got time because my student graduated. He's working in Dassing now. Okay, and it's a very good question because anything you have any asymmetry there, it's possible, you know, to have that kind of thing. But one thing I would like to mention that when you have asymmetry there, the armature reaction, yeah, Usually it's one side increasing, one side decreasing. Yeah, it depends on the design. You could make it even better. Yeah, we know armature reaction in one pole, right? One side enhance, one side weakening. But then if we got the asymmetry there, one side got more reluctance, one side got the less reluctance, then the armature effect will be more uniform. Then will be better. So it depends on the design. That's only from my knowledge. But we didn't do that investigation. Okay. Oh, next one, I think you're only saying wonderful presentation. Thank you very much for that. And a question there. Can you please comment about the torque density of the machine developed by Sheffield and Mitsubishi? I didn't do the calculation, I'm afraid, because we designed the machine under the same, exactly the same machine size. Then we just compare the torque. Okay, and if you want to know the number, it's a bit meaningless because ultimately the torque density also rely on the calling, techniques kind of things there. The calling is very important. But here, personally, very confident our comparison is very, very fair. The reason is all based on the same machine spec, same machine size, same amount of magnet. Then one showing torque is higher. So what you can see is from the data I already provided, if you find out how much is Toyota Prius torque density, then ours definitely got improvement there, right? Very good questions.
Yeah.
Thank you.
Yeah,
Thank you to all of you, and very good questions.
Thank you, Professor Zhu, for the presentation and for your answer. So yes, I think we have covered all the questions we had today.
Maybe I can add some question if you want, Professor Zhu.
Yes, Didier.
Yes, thank you. So thank you, Professor Zhu, for this good and nice presentation. So it was very, very interesting for me. But I have some questions regarding the rotor shape. So I see that you present different topology of rotors. So you also show the asymmetric rotor shape. So I want to understand the effect of this asymmetric shape on the NVH calculation.
The temperature effect.
Yes, on the NVH. So the impact of the
NVH, that's a noise vibration. I think we already got one answer. We already got one question early on. Yeah. As I said, I didn't do that calculation about the vibration, and but I personally believe potentially got a good scope there because the asymmetric there, and then you can counterbalance that armature reaction. There's a possibility there. I didn't do it, so I'm only just guessing. Yeah, and you need to make sure not to do the opposite side, like armature side. If you more affected, then you try to get the more try to enhance it. That would be a problem. Yeah.
Yes, of course, because I think the asymmetric rotor shape will also impact, the gyroscopic of the rotor and also the stiffness matrix. So it will be good if we can maybe analyze so the mechanical behavior.
A mechanical behavior, we all have analyzed it. We have done all the mechanical stress analysis. And in fact, you can look at my paper. And over there, we have also compared the temperature. We compared the mechanical stress. Those is no problem because you can see the geometry, they are quite similar to the conventional one. Yeah, if you look at the one we have two, this side, the one that side there, and we have analyzed all that because the only difference is this side a little bit. But you also need to bear in mind that side of the magnetism became a lot more smaller. Yeah, a lot smaller. Although you got the two there, but it's smaller, so the stress is not that severe and comparatively. So this we have done that. Yeah, just the vibration we haven't done that. Vibration noise we haven't done that, and the losses we also have done that, and because the same amount of magnet is the same, but then you divided that into two small ones, that the loss inside there will be a lot less anyway.
Yeah, thank you for that. Thank you.
A very good question, by the way, and all aspects they are all very important. Well, how to say? I could say problem. One thing, all my PhD students, they all supported by the company, right? We always have a project. It's not saying somebody supported by their family, and then we have more freedom to do whatever we want to do. And another one is, you know, as a PhD, you always have a limit of the time. And this student did excellent research with me. In fact, he already got 1 PhD before joining me. So I was very lucky, and I should thank him, you know, for him to study a second PhD with me. And if he started only 1 degree right from the beginning, then obviously I need to training him very basic knowledge for research as well. And then we wouldn't able to achieve like this. And in fact, I'm only showing 3. And I think he proposed about 5 topologies, and I'm showing those the performance a good one. Another one I already mentioned is the combination of the V-shape and also the spoke. Then you try to make asymmetry. Then after that, the optimization shows that the V-shape and then that spoke one is almost attached together. And then I didn't show further because I personally think that one we need to solve the mechanical problem first, and otherwise they all in like a segmented rotor. Initially, I was quite happy because segmented rotor is also not easy. You can see a lot of segmented stator, but the rotor is not easy. You need to bring them together. About the mechanical integrity, you also need to think about it as well.
Okay. So thank you, Professor Zhou.
You're welcome.
So we have already exceeded the time we had, but I think this is also because you had a lot of very interesting information to share. So it was very nice. So I propose you to stop this webinar now. And I would like to thank you again, Professor Zhou, and to thank you all the attendees. Don't hesitate to join the next PowerAssist webinar. You can visit the PowerAssist website to know the next webinar we are organizing. And so, yeah, I say see you next time.
Yeah, I would like to take this opportunity to express my gratitude to a lot of thanks, many thanks to GEMAC and PowerAssist and for your well, support at Sheffield, and also for your excellent service. And all my students also at the Sheffield, the colleagues, they all appreciate your very prompt technical support and very impressive. And also I do see the GEMAC software now is get to become better and better, and our student using GEMAC more and more. I think almost all our students is using GEMAC now, honestly speaking. Although very often they probably can master several, and but I think GEMAC is very popular. And as I mentioned, the technical enhancement and technical support from GEMAC and PowerAssist is fantastic. And thank you very much. And also thank you for inviting me to give this seminar. I always enjoy it. Thank you.
Thank you for nice feedback, Professor Zhou. Yeah, we try to do our best to support you as well as all the GEMAC users, of course.
Yeah, thank you. I have another meeting.
Yeah. Thank you for your time anyway, everybody.
I have an interview and after this, so I need to leave to join the interview.
So good luck for this interview then.
Yeah. Bye bye.
Have a nice day, everyone. Bye bye.
Bye bye.